Hi guys, welcome to our 50th chapter in control engineering, and this time we are looking at the stability of our control systems. What determines the stability and methods of assessing stability. As usual, Engineer Motion Marfu is my name. For any communication with me, motionmarfu60@gmail.com is my email address, or can come via WhatsApp, social media, +263 717 535 866. Because this is our 50th chapter, we now have covered almost all the basics of control engineering. So I know you are going to enjoy this one. Let us go. You remember the word BIBO from digital signal or processing, which means bounded input, bounded output. What this simply means is for a bounded input, we must get a bounded output. So we talk of a system that is bounded input, bounded output stable. That is to say, if for every bounded input we get a bounded output, then our system is stable. And we are saying the output of a stable system is kept within the admissible boundaries. Whereas that of an unstable system can even increase up to infinity, which means for a bounded input we don't get a bounded output. We defined what a linear time invariant system is, and we are saying a linear time invariant system is stable. You now know what are the poles of a control system. We are saying the poles of the control system must be in the left plane of the S plane. You know what an S plane is. And what does this mean? It means that we know that S is equals to sigma plus j omega. And we are saying the poles must have real negative parts for them to be on the left hand side of the S plane. What this means is if we have got one pole that is in the right hand side of the S plane, then that system is said to be unstable. Please take note. So we are saying the response of an automatic control system is determined by the roots of the characteristic equation. You remember the denominator of the transfer function. If the poles are in the left hand side, as we have seen of our S plane, then what does that mean? It means that the response of the system to various disturbance signals or to various inputs is decreasing. And if there are poles on the imaginary axis, we've got the imaginary axis and the real axis. Or even if we've got poles that are in the right half of the S plane, we talk of the right half of the S plane and the left half of the S plane. The left is on the left, even from the word, and the right is on the right, which means we've got two halves that make up the S plane. So we say, under this case, we say the response of the system to a disturbance. We looked at the effect of disturbance on our output. So we are saying it's either it is constant if the pole is on the j omega axis, or it is increasing if the pole is on the right half of the S plane. We have got two responses. This is the response of a stable system, and this is the response of an unstable system. You can see what is happening to Y1, and you can also see what is happening to our Y2. So we are saying this is our input and these two our output. So we are saying for a bounded input we've got bounded output. For this is our input, the same applies. So this input is the same as this input, and we are saying take note of this output. It is decreasing. In other words, it is becoming stable. It is becoming a constant or almost equal to our input. The same applies to Y2. It is becoming almost equal to the maximum value, which is the reference input. So we are saying, if the characteristic, guys, you must now be conversant with what is a CE, the characteristic equation. If it has got simple roots that are on the imaginary j omega axis, and all of its other roots are in the left-hand S plane, then its steady-state output, we'll be looking at the steady-state output when we do time response. It is a bounded function. And what are we saying? We are saying this system is called a marginally stable system. We'll be defining this term very soon. This is an S plane, and we've got how many poles? 1, 2, 3, 4, 5. We've got 5 poles. Please, if I didn't emphasize this point, let me do so now. On an S plane, poles are indicated a cross sign or with ends, and are indicated with a 0. So, and please take note that This is the value of S, this is the value of S, this is the value of S, this is the value of S. After solving the characteristic equation, after finding the pores from the characteristic equation, and we are saying any pore that is located on the left semi-half, this is the left half, as you are facing your laptop. And we are saying, for example, this pore is got the real axis only, the same applies to this pore, the same applies to this pore. We know S is equals to sigma plus j omega. This pore is got the real part in the imaginary part. This one is got the real part in the imaginary part, hence the dotted lines. So we are saying, if all the pores are located on the left-hand side of the S-plane, then we say this is a stable system. Hence, we are saying pores of a stable system. On this system, we are saying the system is unstable. Why? It is unstable because of this pore, which is on the right half of the S-plane. So, if a system has got a pore that is on the right-hand side of the S-plane, despite all these other poles, it will be an unstable system because of this pole that is on the right-hand side of the S-plane. Please take note that we can have a system where the poles are on the j omega axis. We'll be defining it. So I hope I've made myself clear. Definitions. What we mean by absolute stability. This is the condition whether the system is stable or unstable. And if it is stable, it is a yes. And if it is not stable, it is a no answer. This simply means it's either it is in or it is out. Stable or not stable. What we mean by relative stability. It is the degree of stability of a system. We won't be looking at relative stability in more detail. We'll be concentrating on absolute stability. So what is we have defined what a linear time invariant system is, and we have said it is stable if the following conditions are met. That is BIBO. For a bounded input, we must get a bounded output, and output is controllable. The other condition is in the absence of input, output must be 0 irrespective of the initial conditions. What is an unstable system? We are saying a linear time invariant system is unstable if, one, for a bounded input the output is unbounded, and if there is no input there is an output, which means the output is not 0 for no input. This means that it produces an output when there is no input. What is an absolute system? This is a system that is stable. Please take note, for all parameters of the system and for all parameters of the... What is a conditionally stable system? Here we've got a condition, and what is the condition? The system is stable for a certain bounded range system parameters. So this is referring to for a certain bounded input parameters. A system can be critically or marginally stable. And what do we mean? We are saying it is critically or marginally stable if for a bounded input, for a limited input, the output oscillates at a constant frequency and amplitude. We know that an oscillator produces a signal at constant frequency and amplitude, and such oscillations are called undamped oscillations or sustained oscillations. So stability or instability of a system is its property, that is closed loop pores of the system. It does not depend on the input or driving condition, but it depends on the pores, location of the pores of the particular control system. And please take note of this point. Input pores do not affect stability of the system. Input pores do not affect stability of the system, but only they affect the steady state output. We'll be looking at steady state when we do time response of control systems. We said pores can be located on the left half of the S-plane or right half of the S-plane, but there's a special case whereby we've got repeated roots that are located purely on the imaginary axis, and for such a system we say it is unstable. and we'll see that in graphs ahead. Please take note of this important point. It is, what is a conditionally stable system? We defined it before, and we said if stability is dependent on system parameters, it is said to be a conditionally stable system. And please take note that from this point we can say we can have poles being located on the j omega axis, and we are saying the system can be stable or it can be unstable. For repeated roots it is unstable. Repeated roots it is unstable, but for non-repeated roots it is said to be marginally stable. Guys, take note, this is important. And this is the left half of the S-plane, this is the right half of the S-plane. We've looked at this. This is an illustration of stability. We are saying this is a stable system, this is an unstable system. It can go there, it can go there, and it has got limited space. This is a marginally stable system. I think you would agree with me. This can remain there because as you go there, it will going up. It cannot go there because it will be going up. We are saying stability is the most important specification of a control system, and every working system is designed to be stable. And if a system is not stable, then it is useless. We've got two stages that a system has to pass through. The first one is called the transient stage. Remember your DC transients when you looked at how a capacitor charges and discharges, and we are saying this happens for a small period of time before reaching its steady state. So we've got two states: transient stage and steady state stage. Naturally, the question comes into play. Will the system reach its steady state after passing through transients? A stable system has to do that, but any unstable system may not be able to do that. Let's have a look at analogy. You guys, some of you have fallen in love. You know what happens during the first days, but after some time you won't do what you were doing during the first days. Why? Because you would have reached what we call the steady state. But in your transient stage, sometimes you couldn't sleep, being head over heels in love. So you are also a system. So we are saying to get the answer of this question, state of stability is of utmost importance. And we are saying if the system is stable, its performance and improvements can be taken into account for further consideration. We have defined what a steady linear time invariant system, how it behaves. And we said it is stable if the following conditions are met: B-ball, and if there is no input, the output must be 0, and this is irrespective of initial conditions. We are going deeper and deeper, and we are saying the effect of location of poles on stability. And we are saying location has got a direct effect on stability, and we know what an S-plane is. And we are saying it is divided into two planes, the left half plane and the right hand plane. And we are saying it also has got the j omega axis. So we are saying we'll start by considering pole location on the left half plane, and we are saying we can have a single pole on the real axis and multiple poles on the single. You know what simple means and multiple means: one pole, many poles. And we are saying we can also have complex conjugates that are simple, and we are going to look at the graphical location on the S-plane as well as the impulse response. And we are saying when the poles are located on 1, 2 and 3, we are saying the system is stable for all those conditions. This is a simple pole, this is a single pole located on the left half plane, and this is for an input, this is the response, and you can deduce this from this equation. What happens as t increases, we'll see that there is an exponential decay, and so we are saying single pole is located at s is equals to minus a. You can have a double pole at a, and this is the behavior of our system, and we say this is a stable system. This is a stable system. You might be asked in an exam to determine the response of a system with a pole located at s is equals to minus a. So it's good that you produce the S-plane and the response together. Please take note, we are saying this is a stable system. Our pole is now on the j omega axis, which means it is along this. This is our j omega axis. This is our real axis, or the sigma axis. This is the symbol for sigma. And we are saying the Laplace transform of that equation is this. And its time response is this. Take note of the small letter g for time response. And we are saying this is a complex conjugate because we've got this imaginary part. So we are saying this is minus a plus or minus jb. This is minus a plus jb, minus a minus jb. And we are saying this is the response. Another one for plus jb and another one for minus jb. And we are seeing the decay. You can try to put the values of t there. As we are increasing t, you will see this decay and also this decay. And please take note that we can have single poles being located on the j omega axis with no real part s in this case. This s is equals to plus or minus jb. This is for plus jb and this is for minus jb. And we are saying it produces this is the oscillation that we were talking about. Constant frequency and constant amplitude. And we are saying this scenario whereby a single pole is located on plus jb or minus jb, we say the system is marginally stable. There is no decay, there is no growth. You see, a single pole is located on the j omega axis, and this is the response. And we are saying it is located at s is equals to 0, and this is the point. And such a system, because it is not growing or decaying, we say it is marginally stable. We can have a double pole at s is equals to 0, and this is the impulse response. Please take note of the equation. This is the Laplace transform of a constant k, and you know this is the Laplace transform of g equals to t. And we are saying this is the response. And we are saying when we have got a double pole at s is equals to 0, the system is said to be marginally stable. Take note. This is an unstable system. Please take note of the response. It is increasing, and it is also increasing in the negative direction, in the positive direction. And this is the response, and this is the location of poles. And these poles are on the j omega axis. In other words, we've got a double pole at plus or minus jb, double pole at this point, and also double poles at this point. And we are saying the system is unstable. Multiple pole simply means double pole. Please take note of the time response and the Laplace transform of this. Then this is also, this now is showing location of poles on the right hand side. We have done on the left hand side on j omega, but we are now assessing the response on the right hand side, or right half plane is the same. This is the left hand side, this is the right hand side. This is a simple pole at s is equals to a, and this is the left half of the right half of the s plane. This is the Laplace transform, and this is the time. This is the inverse Laplace transform. So the Laplace transform of this is equal to this, and we are saying our pole is at s is equal to a, or our s is equal to plus a, and we are saying this is the response. And we know that for any pole located on the right half plane, it is an unstable system. The same applies to this double pole. This is single pole at s is equal to a, double pole at s is equal to a, and you can see the increasing response as t is increasing. So we are saying the system is unstable for all of the above conditions, for a single pole as well as for a double pole. Let's proceed. This pole also is on the right hand side of the s plane. Please take note that this is an equation. S is equals to a plus or minus jb, plus jb minus jb, and this is the response for plus jb. This is the response for minus jb. Please, this is an unstable system. As you can see, for any increase in t, if t increases up to infinity, any stable system must approach the steady state. But this is not approaching the steady state. We'll be doing this more and more, guys. If you're enjoying, if you're learning something, don't be afraid of the subscribe button. Telecom Academy gives you real convenience. Let us go. Effect of location on poles on stability. Pole location has got an effect on stability, and we are saying from the definition of stability, the impulse response must tend to 0 as our time t approaches infinity. Hence, we saw that on this it is not tending to 0, the system is unstable. On this it is not tending to 0. Also on this it is not tending to 0, hence the system is unstable. It is not tending to 0, but it is also not increasing, hence marginal stability. It is tending to 0 on this, but on this one it is not, it is remaining constant, hence marginal stability. So that is what we mean by that statement. So we are saying we can draw the following conclusions. This we have done, guys, and we are saying for all poles located on the left half of the S-plane, impulse response tends to 0 and hence system is stable. 2, for poles on the j-omega axis and there is only one pole, system is marginally stable and or is of limited stability. And we are saying for all poles located in the right half of S-plane, and if there is a repeated root, the impulse does not tend to 0 and it increases with time. Therefore, the output becomes unbounded. Hence, the system is said to be unstable. Therefore, stability, we know that stability of the system is determined by pole location. The roots of the equation have a negative real part. If the roots of the equation have a negative real part, system is unstable. If they have got a 0 real part and the pole is not repeated, it is marginally stable or it is of limited stability. If they have got, please take note of this important point, if they have got a positive real part, the system is said to be unstable. Guys, don't hesitate to hit the subscribe button if you are getting such data. A question. Determine whether the following systems are stable, marginally stable, or unstable. Number 1. The poles are on -2 and -5. We say the system is stable since both roots have negative real parts. Please take note. In one root is -3, the other root is 2. Because of this, we say the system is unstable since one root has a positive real part. In other words, it will be on the right half of the S-plane. -2 and 0. The system is marginally stable because the roots are non-positive. Please take note. -2 plus j, -2 minus j. And we are saying, since the negative real parts are only counted, the system is stable. What are we saying? We are saying we don't consider the plus j and minus j. We consider -2 and -2. So the two roots are negative. Hence the system is said to be stable. -2, take note that we've got a 2 there. So we simply, because of this positive real part, we say the system is unstable. -2 plus j4, -2 plus j4. Because of -2, the system is stable. -2 plus j2, -2 minus j2, -2j minus 2j. This system is marginally stable. Why? Because of the 0 part there. These are located on the j-omega axis. We only have the imaginary part and the real part is 0. You can proceed to the next slide. An integrator, the characteristic equation of an integrator is equals to 0, and we are saying since there is no root with a positive root part and because of s equals to 0, it is marginally stable. We'll be looking at this in one of the courses ahead or in one of the chapters ahead. For step input, we know a step input gives, this is the Laplace transform of a step input, and we are saying the system is marginally stable. Then for J, a bounded input, J is a bounded input that produces a bounded output. The system is unstable. Take note that this is a sinusoidal signal and it has got constant frequency and constant amplitude, hence the system is marginally stable. For this, the system is stable because there is a decay in the exponential function. stability concept, and we are saying a linear time invariant system is said to be stable if the following conditions are met. Bounded input produces bounded output. This is revision. Let's have a look at the stability of a linear closed loop system can be determined from the locations of the closed loop poles in the S-plane. This is a transfer function, and this is equal to GS, and we've got this transfer function, and we are feeding this system with n step input, and the Laplace transform of the step input is equal to 1 over S. So how do we determine the response of this system? This is the transfer function multiplied by the input, which is 1 over S, and this is our equation. We're going to express this in Laplace transform, so it's going to be A over S plus B divided by S plus 3 plus C divided by S plus 5. Guys, we did Laplace transform, and after finding A, B, C, this is A, this is B, and this is C, and if we simplify this, it's going to be equal to this. We are going to find the inverse Laplace transform. Guys, don't forget the application of Laplace transform in control systems, and this is our inverse Laplace transform. And guys, take note that this is decaying, this is decaying, and we are saying as t approaches infinity, our system response must approach the steady state, which is called CSS. So we are saying both exponential function this and this approach 0, and the output will be a steady output, which is equal to this, and such a system is called an absolute stable system technology. This is our transfer function, and this is our input. How do you calculate the system response? The system response is equal to the gain, which is the transfer function multiplied by the step input, whose Laplace transform is equal to 1 over S. So this is our equation. We are going to express this in Laplace transform. It's going to be A over S divided by plus B minus B divided by S minus 2 plus C divided by S plus 4. We are going to find A, B, or C. A is equal to this, B is equal to this, C is equal to this. We are going to find the inverse Laplace transform. This is our inverse Laplace transform. Please take note that we have got this part there, which is positive. We are saying due to pole located in the right, this is located in the right half, there is one exponential term with a positive index, like this in the transient output. So because of this, the system is unstable. Please take note. So guys, you must be able to prove for a given input to determine whether the system is unstable or not. Guys, we are now approaching the peak of our control system stability video presentation or topic, the Routh-Hurwitz criterion. These are two guys, Routh and Hurwitz. They combined and they worked together and devised a method of determining the stability of a given characteristic equation or of a given system. We know that the transfer function is given by this divided by this, and we know that A and B are constant. And we know that when we want to find the poles, we take note of the characteristic equation, and this is defined. This is derived from the denominator polynomial, and this is equal to this. We have set it to 0 so that it becomes a characteristic equation, and we are saying the roots of this characteristic equation represent the closed loop poles. The stability of the system depends on their location. The necessary but not sufficient conditions, we took note of this, is that all the coefficients of polynomial must have the same sign of B0, B1, blah blah blah, and we are saying all the powers of S must be present in a descending order. You can see the descending, and please take note that the above conditions are not sufficient. So what are we saying? We are saying the Routh-Hurwitz criterion is an algebraic method of determining the stability of a linear time invariant system. The criterion, it provides an information of whether the system is stable or not depending on the position of the poles. That is, whether they lie on the left half of the S-plane or on the right half of the S-plane. It can also be used to determine the limiting values of a variable parameter. We'll be looking at this when we do the root locus. This is our characteristic equation with the descending powers of S. And A0, A1, blah, blah, blah are our constants. So we we have exhausted this, the left half of S-plane, and we are saying if the pole is located in the left half, the system is stable. On the right half, the system is unstable. On the j-omega axis, the system is marginally stable. So we are saying Hurwitz and Routh independently published the method of investing the sufficient of stability of a system. This guy, his method or his criterion is in terms of determinants, while Routh criterion is in terms of the array formation. So we'll be combining the two to determine the stability of a system. The disadvantages of Hurwitz's criterion, guys, take note that I didn't go deeper insofar as Hurwitz's criterion is concerned alone, because the combination of Routh and Hurwitz is one that is being used. So these are the disadvantages. It is very complicated and time consuming for solving higher order systems, and this method is unable to find the exact number of poles located in the right half of the S-plane. It is very tough to predict marginal stability. So we are saying due to the above disadvantages of Hurwitz's criterion, the method suggested by Routh, known as the Routh's method or Routh's criterion, is used. And because there is a combination of what was discovered by Hurwitz and Routh's array, it is called Routh-Hurwitz array method. And let us go straight into it. We are saying this is what we call the Routh's array, and we'll be using the determinants method. So taking into consideration Hurwitz's criterion, and we are saying this is our characteristic equation. It is equal to 0. Take note, and we are saying this must be decaying. S must be in decaying powers: n minus 1, n minus 2, n minus 3, etc., etc. And we are saying these are the coefficients for even and the coefficients for odd. A0, A2, A4, A6. These are the coefficients for even. Then these are the coefficients for odd, which is A1, A3, A5, etc., etc. Then from B1 we are now finding the determinants. And how do you find the determinants of B1 with the coefficient B1? This is A1, A2 minus A0, A3 divided by A1. How do you find this B2? Please take note that this is equal to 4s to the power n minus 2. For B2, where is our B2? This is our B2. Is A1, A4 minus A0, A5 divided by A1. And we do the same for B3, B4, even up to C1. You can do that for C1. How do you find the... So we are saying the coefficients of B1, B2, B3, etc. and also C1, C2, C3, etc., D1, D2, D3 are evaluated in this way by finding the determinants. Hence, we are taking note of the Hurwitz criterion. The coefficient of A0, A2, A4, then the next line for the odd ones, A1, A3, AN5, the coefficient of B's, C's, D's and E's up to the last power or the least power. And we are saying this is how you find the coefficient of B's, B1, this divided is the determinant of C1, the determinant D1, D2. So we are saying B1, B2, C1, C2, D1, E1 are computed as above. And we are saying according to Routh's stability criterion, a system is stable if the terms of the first column, this is our first column, tabulation are of the same sign. Whenever there is a change in sign, that change in sign is caused by poles that are located on the right half of the S-plane. We are going to see that. Take note of the following on Routh's criterion. We are saying the number of roots of the characteristic equation that are on the right half of the S-plane is equal to the number of sign changes of the coefficients in the first column of the Routh's tabulation. We are going to see that when we do some examples. We are saying if a system satisfies Routh's criterion, it means it is absolutely stable. Then it is desirable to go further and define its relative stability. We are not going to to do that. So we are saying the greater the distance of a pole from the j omega axis, guys, you know the j omega axis, the greater is its relative stability. We will not go into analyzing the relative stability of a control system. We only dwell on absolute stability, and we'll do that using Routh-Hurwitz criterion. Special cases of Routh-Hurwitz stability criterion, and we are saying if a special term on the first column, guys, you understand the significance of the first column is 0, while all the other terms of the row, which is of the row, please take note that we are not referring to the row, are non-zero or do not exist, then the 0 term is going to be replaced by a very small number which is of the same sign as the previous terms, the first column. And the procedure is going to be continued as normal. Or alternatively, I will dwell on this one. Alternatively, the characteristic polynomial can be multiplied by s plus a. Please take note that some authors say s plus m, and this a must be greater than 0. And please take note that minus a is not a root of the characteristic equation. We are going to have an example whereby we're going to multiply the characteristic polynomial by this and proceed with the Routh-Hurwitz criterion. Please take note of B, which is under special case. If all terms of a row in the Routh-Hurwitz array are 0, then the array is completed by replacing the 0 terms by the terms of the differential. We are going to differentiate the auxiliary equation of the previous row. It will become clearer when we solve an example. Then the third special case, if 2 or more rows have 0 terms, then the system is unstable and the characteristic polynomial has got 2 real poles with multiplicity of 2. We are also going to have a look at the examples that include these special cases. Let us. This slide is a repetition, and we are saying the process is continued until s to the power n is obtained, which is equals to an, and we are saying the stability of the system can be predicted from the array as below. And this is an important point. All the terms in the first column of the Routh array should have same sign, and there should not be any change of sign for it to be stable. And this is a necessary and difficult and sufficient condition for the system to be stable. Any change of sign in the first column of Routh's array or tabulation indicates, number 1, the system is unstable. Number 2, the number of changes of sign gives the number of rows, I've said this, that lie on the right half of the S-plane. And we are saying any root that lies in the right half of the S-plane shows that the system is unstable. So we are saying if you are asked to state Routh stability criterion in words, this is how you state it. The system is stable if and only if all the elements in the first row have the same algebraic sign. If all the elements are not of the same sign, then the number of sign changes of the elements in the first column equals the number of roots of the characteristic equation in the right half of the S-plane. Please take note. This is how you state Routh stability criterion. And we are saying the criterion applies for a system. The criterion implies that for a system to be stable, there should not be any changes in the sign in the entries in the first column of the table. Guys, don't sweat over this. Once we do 1 or 2 examples, it will be clear. And we are saying this is a both necessary and sufficient condition for ensuring stability. We have looked at the distinct cases, and we call them the special cases from this slide, and we are saying go through them and see if they make sense. They are just the same as the special cases. An example: determine the characteristic equation of the following system, and this is our system, this is our g of s, this is our h of s, and we are going to determine the characteristic equation. It is equals to 1 plus gs times hs, and it is equal to 0. We are going to calculate our gshs. We are going to multiply this, and this is going to be our ghs, our 1 plus. And please take note that, so what are we saying? This is our h of s, and this is our gs. This is our expression, and this is our hs. If we multiply the two, we are going to, it is equal to this. This is the characteristic equation. We are done. We have finished. We are also number 2, we are given this is our g of s, this is hs, and it is equals to s. So we are going to form the characteristic equation according to our question, and so we are going to multiply this, which is equal to g of s multiplied by s. This is our characteristic equation. So this is correct, or this as it is also correct. We have only simplified this to get this, but it is also a characteristic equation. Then the third question is, this is our g of s, this is our h of s. So we are going to multiply this, which is our g of s multiplied by our h of s, which is equals to this. So this is our characteristic equation, or this one. It is also our characteristic equation. Must be able to simplify from there to another question. Examine the stability of s to the power 3 plus 5s squared plus 10s plus 3 is equals to 0. This is a characteristic equation, and we are told to use Routh-Hurwitz method or Routh-Hurwitz stability criterion. This is our A0, take note that, and this is our A2. This is our A2. This is our A1, and this is our A3. Please, guys, take note of how you build Routh-Hurwitz tabulation or array. So we are now going to calculate B1, and please take note that, sorry, this is equals to b to the, this is s to the power 1. Let me see. So this is our B1, B2, this is our C1. Please take note of Routh-Hurwitz array. So how do you calculate B1? B1 is 5 times 10 minus 1 times 3. And this is going to give you 9.4, so we are going to put 9.4 there. How do you calculate B2? B2, take note that we've got some zeros there, and hence 5 times 0 minus this gives you a 0, hence this 0. We are now going to calculate C1, and C1 gives you 3, and this is your 3, and you are done. So let's look at the coefficients in the same column. They've got the same sign, so it means there is no pole that is on the right half of the S-plane, hence the system is stable, and we are done. In the first column there is no change of sign, hence therefore the system is stable. So we have examined the stability of the system. And another example, slightly different, examine the stability of this system, and this is a characteristic equation, and we are going to form Routh-Hurwitz array. Please take note that the highest power of s up to the least power of s, and we are saying A0, A2, coefficients of this, coefficient of this, coefficient of this is 2, coefficient of this is s to the power 0, is this. So we are not going to calculate B1. B1 is 2 times 3 minus 1 times 10. This gives you minus 2. So we put a minus 2 there. This is equal to 0 because there is no term. There is a 0 there. There is a 0 there. There is also a 0 there. How do you calculate C1? C1 is equal to minus 2 times 10 minus 2 times 0 divided by minus 2. It's going to give you a 10. Hence this 10. So we are done, but please take note that there is a change of sign there. So it means that there is one pole that is located on the right hand side, in the right hand side of the S plane, or right half of the S plane. So we are saying there are 2 changes of sign in the first column. We've got a 2 minus 2, so there's a change of sign. Then from there there's a change of sign. So we are saying from 2 to minus 2 and from minus 2 to 3. Hence we say the system is unstable. Then a question says, how many poles are located on the right half of the S plane? This is for you. And another question, we are asked to examine the stability. We are asked to find to determine the suitability, and we are going to use Routh-Hurwitz stability criterion. So we will start, this is 1, we'll start with this one, and we are saying s to the power 4, these are the coefficient of the even powers of s, so we are going to save 1, 21, and 20, this is s to the power 0. Then we'll go to coefficient of the odd powers of s6, let me correct there, 36 and 0. This is our B1. We are going to find the determinant is 6. There's an error there, I don't know what happened. This is 15. So this is our B1. Go to our B2 is 20. If you solve this one, you get 20, so we are going to put a 20 there. You go to C1, our C1 is 28. You go to D1, our D1 means is 20. So we have now populated our Routh-Hurwitz table, and let us evaluate it now. If you ask it to evaluate, we are saying there is no any in the first column, there is no change of sign, hence the system is stable. All the coefficients of this equals to 0 are positive and no coefficient is missing, hence the system is stable. This is the statement. Check the system represented by the following characteristic equation for absolute stability. This is our characteristic equation. We are now going to form Routh-Hurwitz array, Routh-Hurwitz table, and this is 1, A0, A2. There's an error there. This is 5. Coefficient of A1, coefficient of A3 of s to the power 0 is 10 there. We are now going to find B1. Coefficient of B1, 5 times 25 minus 10 divided by 5, 23. Coefficient of C1, this is 10. Then the coefficient of C2 is 0. So we are saying all the elements in the first column are positive. There's no root in the right half of the S-plane. Therefore, the system is absolutely stable, and we are done. Examine the stability of this using Routh-Hurwitz criterion. And S5, the coefficient of S5, this is the meaning of A0, A2, A4. Coefficients for even, the coefficients for odd. We are now going to find C1. C1 is equal to 0. Guys, you can calculate. C2 is equal to 2.5. C3 is equal to 0. But D1 is equal to infinite there because you divide by this 0. So we are saying Routh-Hurwitz array has failed when we get infinite. So what are we going to do? We are going to remove this difficulty by following two methods, of which one is going to be discussed. And this is discussion. Right, this is the method that we are going to discuss. We are going to put s is equals to 1 over z, and the polynomial is going to become this. If you find the common denominator z5 there and you simplify it, you are going to get this expression. So we are now going to form a Routh-Hurwitz array from these expressions. After forming a Routh-Hurwitz array, this time in terms of z, you will see that 1, 8, and 2, A1, 3, 4, and 1. Then we are now going to find C1 up to C1, D1, E1, etc. So this is going to be 6.67. You can prove this. C2 is going to be this. Then our D1 3.25, our E1 minus 0.382. Take note there's a change of sign there, and the next one is close to 1, meaning there we've got 2 poles that are located on the right half of the S plane, because we have had a change in sign twice from positive to minus and then to positive. Hence we can say there are 2 changes of sign, hence the system is unstable. Guys, take note of how you simplify. This is the method that I've decided to teach you, but you can look for the other method on your own. Alternatively, you can multiply the original expression by s plus a, where a is a positive real number and it is simple to use 1. So we are going to multiply s plus 1 by this expression there. This is our expression. So after multiplying, this is going to be the resultant or the result. So we are now going to populate the Routh-Hurwitz array table using these coefficients 1, 5, 11, 3, 12, and 1. We are now going to find C1, C2, D1. This must be. So our C1 is equal to 1, this 1. Our C2 is equal to 2.67. Obviously, this is 0. Then our D1 is minus 20. Take note of the change of sign. Then our D, this one is a 0. And also, this is our E1, 10.67. If we proceed, this is going to be our 1. So you can, we are now concluding that there are 2 changes of sign, hence the system is unstable, which is the same result that we found when we substituted s by 1 over z. Problem on a Routh-Hurwitz criterion, and the question goes: examine the stability of s to the power 5 plus 2s to the power 4 plus 2 times s to the power 3 plus 4s squared plus 4s plus 8 equals to 0. This is a characteristic equation. This is A0, the coefficient is 1, A2, the coefficient is 2, then A4, the coefficient is 4, A1, the coefficient is 2, A3, the coefficient is 4, and A5, the coefficient is 8. We are now going to find D1, D2, and D3. We now have a special case, and we've got all zeros. And when we find a row with only zeros, we say Routh-Hurwitz array has failed. So what are we going to do? We take cognizance of the row above and form an equation by using the coefficients of the array which is just above the row of zeros. This equation is known as the auxiliary equation. And after doing that, how are you going to proceed? We are now going to form an auxiliary equation, and this is the equation, and we are going to differentiate it. After differentiating it, we are now working with this one. So we are now going to put the coefficients. So it's after differentiating, it's going to be 8 times 8 s to the power 3 plus 8s squared, which means that the coefficient of s to the power 1 is 0, and also the coefficient of s to the power 0 is 0. So we are now going to put the coefficient. This is 8, 8 and 0, and we are now going to find C1 using the determinant method. And after proceeding, this is D1, C1, E1, and F1. We are now going to evaluate, and when we are evaluating, we take note of this first column. We've got two changes in sign, from plus to minus, from minus to plus, and we can safely say the system is unstable. And guys, this is for you. This is for you, and ignore it to your own peril. Ignore it to your own peril. And guys, this is the end of our chapter on control system stability. And our next topic will be on root locus method, which is a method for assessing the stability of control systems when the gain, which we are going to call K, is varied from 0 up to infinity. Until then, guys, it's bye for now. And if you are learning something, if you are enjoying your videos, don't be afraid of the subscribe button. Hit it.